Hello friends, today we are going to solve the questions from rotational motion. This question is from the year 2021. We are going to solve only one question, and that is from the advance. It states that a pendulum consists of a bob of mass m 0.1 kg and a massless inextensible string of length 1 meter. It is suspended from a fixed point of height h 0.1 meter above a frictionless horizontal floor. Initially, the bob of the pendulum is lying on the floor at rest vertically below the point of suspension. A horizontal impulse P 0.2 kg per meter per second kg meter per second is imparted to the bob at the some instant. After the bob slides for some distance, the string becomes taut and the bob lifts above the floor. The magnitude of the angular momentum of the pendulum about the point of suspension just before the bob lifts off is J kg meter square per second. The kinetic energy of the pendulum just after the liftoff is k joules. The value of k and j and k we are supposed to find out. So in this case, we have to remember that the length of the string is, you can say, on the longer side about the height where it is fixed. Okay. So if you draw the approximate of the figure, if suppose it is lying on the frictionless table, and this table, its height is 0.9 and the pendulum is lying on the, you can say, this table. Obviously there will be this string, we can just represent it like this, so that this entire length comes as 1 meter. And once it is struck by impulse from this point, it is going to drag up till some distance, suppose somewhere here, and this particular instant the string becomes taut. Okay. Now it is going to take a lift off like this. This is the basic meaning of this. Let us suppose this is m and this is mass m, position is A and this position is B. Okay. So it is not going to immediately lift off, it is someone going to drag, suppose point up till B, then it is going to lift off. Okay. So, and this is point O, and let us assume that in the coordinate system this point O is called as 0, 0, and the point on the floor, this is point A, it will be called, it will be minus 0.9. Okay, so we can call this as 0. This will be 0, minus 0.9. Okay. And A is the initial position of the bob. We have to remember that. A is initial position of bob. And if B is the final position, and we can just mark the axis, and suppose this is our y axis and this is our x axis, and if we between A and B it drags about a distance of x, then we can say that our B is going to have a position of x 0.9. 1 second. Yeah, and at this particular instant this string will be taut and its length will be completely 1 meter. Okay, at this position it cannot be 1 meter, here it will be 1 meter. Okay, that was mistake my part. Okay, at this particular instant the length will be only 0.9. Okay. So let us call this string length as L. L is our string length. Okay, and we say that, and this length is given to us as 1 meter, and we say when the string is taut, string is taut, the bob's position is our B, and the coordinate of is our x minus 0.9, and this position must satisfy, you can say must satisfy the constraint and that constraint is our, we can use just Pythagoras theorem, because this is point O, this is A, and this is B, and this we know is about 0.9, and this is a 1, and this we called it x. So we can say should satisfy the constraint, and that constraint is our x square plus 9 whole square should be equal to 1. So from here we can say that our x will be approximately equal to plus minus 0.4358 meters. Okay. So like we assume that the impulse is in this direction, so we are going to take our x will be equal to you can say impulse is in positive x direction, and that impulse is our p, and whose value is given to us as 0.2. And another part that I mentioned, that our floor is frictionless. Okay. So let's find out velocity after impulse. Velocity after impulse, and for that we can use the formula that our P is equal to m into V naught, and P is our 0.2, mass is our 0.1 times V naught, so this gives a V naught is equal to 2 meter per second. So it means it is going to slide horizontally with the velocity 2 meter per second. So we can say that bob slides horizontally with velocity because it is in x direction. So let us call this as our v of x is equal to v naught, which is equal to 2, and our vertical velocity will be equal to 0. Okay, and this is before this point B. Okay, because it is sliding from A up till B. This motion is along the table. And now we have to find out, or rather we can say that position and velocity when the string becomes taut. It means our at point B. So we can say position and velocity when string becomes taut. Okay. And we are considering the positive from momentum, the impulse is acting towards positive x-axis. So for that, let us assume that value of x is positive, and that is our 0.358 meters, which we just calculated. And now the the floor is frictionless. You can say floor is frictionless, therefore the horizontal velocity remains same. Horizontal velocity remains same. That is Vx is equal to 2 meter per second. Okay, and we have to remember this is up till just fraction of behind B. Okay, because there is no forces acting on it. There will be no tension because string is not taut, or we can say it is not tightened, and there is also no friction. So this Vx will be same. Okay. And you can say that at the instant string becomes taut, or we can say this is just before liftoff. Just before liftoff, the coordinates, we can say the bob is at x comma y, which is our square root of, we found a 0.4358 comma minus 0.9. Okay. And with velocity because velocity in vertical direction is 0, so we can say velocity it will be over 2 comma 0. Okay. And now we have to find out the angular momentum about point O just before liftoff, and kinetic energy also just after liftoff. Okay. One is before, other one is after. So let's find out angular momentum. Just before liftoff. Just before liftoff. And we can use the basic. We know that angular momentum about the point of suspension, that is O, angular momentum about point O, whose coordinates are given as 0, 0. That is our L is equal to our R cross P. And our P is our mass into velocity, that is a momentum, and R is the position vector of the bob. And therefore we can say that our R at point just before liftoff, that is point B, is having a coordinate of square root of 0.19, and this is minus 0.9. And our velocity is 2, 0. Therefore, our momentum P will be equal to mass, this is 2, 0. Mass is 0.1, 2, 0. This giving us 0.2, 0. Therefore, angular momentum. Therefore, our which we wrote as our R cross momentum P, and we can write it as our position vector is R plus xi plus yj cross pxi plus pyj, because py is 0 and our, so this goes away and we get that momentum in x direction will be equal to over x p this will be px multiplied by x and px multiplied by y, cross product, sorry. Okay, so we get this as our we have x into px, and we have our I cross I plus y into px, and this we have j cross I, and we get that our L of x will be equal to, this will be our minus, and y is our minus of 0.9, p of x is our 0.2, and okay, it's magnitude only, it doesn't matter. So this will be coming as 1.8, 219, and this will be coming as 0.18. So just before liftoff, which is our J, and magnitude. J is 0.18, 0.18. Now we come to our kinetic energy. So we have to find out the velocity just after liftoff, because kinetic energy is after liftoff. So we need the velocity just after liftoff. Okay. Now, as soon as there is a liftoff, there will be tension in the string. Okay. And there will be, because of this, the velocity of the, you can say, bob is going to change. Okay. But we know that our impulse is instantaneous, so we can use the angular momentum conservation. Okay. And okay, first of all, let's check about the velocity part. Okay. And one thing for sure, we know that velocity before liftoff just before liftoff is our Vx, and that is our 2,0 meters, and it is along the horizontal direction, that is x direction. Okay. And as string becomes taut, the tension impulse enforces the pendulum constraint. That is, the velocity must be perpendicular to the string, or simpler terms we can say tangential to the circular path about O. Tangential to the circular path about O, which basically means that as soon as the string becomes taut and it is going to lift off, so this will try to follow a circular path, so the velocity will be in this direction, that is our tangential, so it will be just 90 degree. Okay. And we already know that the initial position is our O, and this is our A, and this is our B. So we already know their position vector. And based on this, we can write that the string direction from bob to O. So we can say string's direction from Bob here it is point B to O, and we can say that is our push vector R will be equal to square root of 0.19, and this is minus 0.9, which we already written also. Now we can find out the unit vector along the string towards O. Unit vector along the string towards O. And that is suppose our R unit vector, which will be the magnitude and its square root, and the numerator will be the position vector, that is our and 0.9, and the denominator will be coming as this is 81 plus 0.9 will be equal to 1. So we are going to get this as minus square root of 0.19, and this is 0.9. So just after liftoff, let us call that velocity is v after. It is going to have two components. In x direction, let us suppose v x prime, in y direction our v y prime. Okay. And this v after, like we said, this will be our v after, and it is perpendicular. Okay, so the dot product in the string direction will be equal to 0. So you can say this v after is perpendicular to the string. Therefore, dot product of v after dot is our R unit vector should be 0. And from here we can write that our square root of 0.19 vx prime plus 0.9 vy prime is equal to 0. So from here we get that our vy prime is equal to our square root of 0.19, and this is our vx prime, approximately 0.484 vx prime. Now we can use conservation of angular momentum about O to find out our horizontal, that is our vx prime. So we can say conservation of angular momentum about O to find vx prime. And let us suppose that our angular momentum Lz prime is equal to our x py prime minus y p prime x, and we get this will be equal to our 0.19 multiplied by mass v by prime minus of 0.9 and mvx prime. We can take mass as common, and this gives us 0.19 vy prime plus 0.9 vx prime. We can substitute our vy prime, so we get this as Lz prime will be equal to mass square root of 0.19 multiplied by 0.19 divided by 0.9 vx prime plus 0.9 vx prime, and this gives us that our m is equal to 0.19 vx prime plus 0.9 vx prime, and our mass is 0.1. So we get that our Lz prime is equal to 0.1 divided by, this will be 81 once again 1, and this is vx prime divided by 0.9. Okay, so we can write this as 0.1 divided by 0.9 vx prime, and equating before and after angular momentum, which we just found out. That is, I think I made a mistake here. This is z, not x. My mistake. So we equate them. Equating Lz is equal to Lz prime, which gives us 0.18 is equal to 0.1, 0.9 vx prime, and this gives us that our vx prime will be approximately equal to 0.784 meter per second. Now we can just find out the kinetic energy. Therefore, kinetic energy just after liftoff. K is equal to our half m vy prime square. Sorry, it is going to have two components, my mistake. So we found out v pi prime, and this will be here v after whole square, and v after x component is our 1.62, y component is our 0.784. So we get that our K is equal to our half mass, and this comes as our Vx prime square plus Vy prime square. So this will be half into 0.1, and we have 1.62 whole square plus 0.78 whole square. So we get that value of kinetic energy approximately equal to 0.162 joules. So this comes as 0.16 joules. So this completes the question. Thank you.